Alright, let's have a look at this one. So, the minute we see this integral right here, so number one, which method is the best to evaluate this integral? Did you try maybe U substitution in this case? No? Well, looks like U substitution is not going to work, right? Because the quantity inside of the radical, it's not 1 degree higher than this y outside of the radical, right? Okay, so I'll take that. However, U substitution, it's still going to work. So, however, in this case, well, there's a couple of ways to do a U substitution. The usual one, the one that we do pretty much every day, which is what I call the 2-ingredient U substitution with the U and the du, right? But there's another one that, in this case, we use a third ingredient, which I'm going to show you how do we do that. So let's see. So U equals to 1 plus y du. Okay, so that's number one ingredient. Du equals dy. So let me label this as number one, number two. So the third ingredient in this case that we need is solve for the variable, in this case y equals u minus 1. So that's number 3. And this is a good trick to, this is a good way around this issue when you don't have 1 degree less outside of a radical, exponential, or anything, you know, or parentheses. So what we're going to do in this case is replace. So the integral from 0 to 3. So actually I should change the limits of integration as well. Let me do that as well. So u of 0 and u of 1. So u of 0, that's 1 plus 0, and u of 1, that's 1 plus 1. So that's going to give us 1 and 2. That's going to give us the integral from 1 to 2. Alright? Yes?
Isn't it 0 to 3?
0 to 3, yes. Okay, yeah, that's a 3. 0 to 3, so that's, yeah, I don't know why. I don't know where I got the 1 from. So, and that's going to be from 1 to 4. Alright? That's going to change a lot. Okay, so let's do the U sub. So that's a 2 pi integral from 1 to 4. And so our y became u minus 1 times the square root of u. And of course, in this case, there remains yes.
Since we're altering the equation, do we have to change the boundaries, or is that also?
It's recommended. I mean, it's optional if you don't change the limits the way I usually do it here. So when you do the U substitution, skip the limits, do the integration, and then after the back substitution, use the original limits, like in this case 0 to 3. But I prefer changing the limits because I skip the back substitution and I can just use the fundamental theorem of calculus just in terms of U. But either way, it should give you the same answer. And How do you do it on the exam? I'm okay either way, as long as you get the same result. Okay. So this is the same. Okay, du 2 pi integral from 1 to 4. So that's u minus 1, u to the 1/2 du. And well, let's use the distributive property here. 2 pi integral from 1 to 4, 1/2. Okay, so that's distribute. That's u to the 3/2 minus u to the 1/2. And well, again, in this case, you don't have to split these two into two separate integrals. So that's fine. Just integrate. So 2 pi u to the 3/2. The integral is u to the 5/2 divided by 5/2 minus u to the 3/2 over 3/2, evaluated from 1 to 4. Before using the fundamental theorem of calculus, let's go ahead and clean the mess a little bit. All right. So number 1, so that's a 2 pi times 5/2, no, 2/5 rather, u to the 5/2. And that's a minus 2/3 u to the 3/2 from 1 to 4. And I think at this point we can actually use the fundamental theorem. Move this a little bit. Yep. So let's see what we get from here. So number 1, I would like to change this into radical form. Recall that there's a couple of ways to rewrite this, and let me write them down on the side. So let me write it down here. Okay, recall by properties of radicals, then whenever we have x to the m over n, this is the nth root of x to the m, or the square root of m, x to the m rather, raised to the n power. There's a couple of ways to do it. In this case, I'm going to use the second version, the very last version, because notice the limits of integration 1 and 4, they are both perfect squares. So what I'm going to do is take the square root first, and then raise to the, to the 5th and to the 3rd powers. Of course, you can do it the other way around if you use this version right here, but you would have to raise the 4 to the 5th power, big number, and then take the square root of the big number. So sometimes when we're doing these kind of operations, for arithmetic operations, in an effort to be more efficient, it's better to simplify first before we expand anything. So I'm going to see my point here. So let's see. So let me change this to pi times 2/5 of, okay, yes, the square root of u to the 5th power minus 2/3 the square root of u to the 3rd power, and from 1 to 4. And we may now plug in the values. Well, in this case, no, that's not going to be enough space. So 2 pi (2/5) square root of 4 to the 5th minus 2/3 square root of 4 to the 3rd minus 2/5 square root of 1 to the 5th minus 2/3 square root of 1 to the 3rd. Alright, and after simplifying all this, what should we get? Well, what's the square root of 4? The square root of 4, which is 2, and then 2 to the 5th power is 32. And then that 32 times 2 is 64 fifths. So I'm going to go to 64 fifths. And then the square root of 4, which is 2. 2 cubed, which is 8. 8 times 2, which is 16. What happened here? 16 times 2. Is that, wait a minute, no. So that's 8 times 2, that's 16 thirds. Minus 16 thirds. And then minus the square root of 1, which is 1 to the 5th. It's also 1 times 2 fifths. It's just going to be 2 fifths. And in this case, negative times a negative is positive. It's just 2 thirds. Alright. And after cleaning this up, we should get 232 pi over 15 as a final answer. Alright. Let me zoom it out so you can see the whole problem, in case you missed any detail. Questions about this particular example? All right, let's do the next one. Okay, so for the next one, we have the arc of the parabola y equals x squared from the point 1, 1 to the point 2, 4. So notice the presentation of the exercises. Sometimes they're giving us values of x, sometimes they're giving us ordered pairs. And the reason for which we are going to do this, they're giving us ordered pairs, is because we're going to do the same problem 2 different ways, just so you can see that depending, or rather regardless of how you set it up, whenever you have like the same region, the same rotation, you should get the same result. Alright, so let's see. They're asking us to find the area of the resulting surface by considering y as a function of x and by considering x as a function of y. So in this case, the direction of the rotation, it is not the one that is changing. It's only how we represent the function. So that means that we are supposed to obtain the same result regardless of how we set it up. Alright, so let's see. Let's do a mini graph. So if we wanted to graph the parabola, well, of course it would look like this, you know. However, we don't want the entire parabola. We just want it from x equals 1 to x equals to 2. So basically only this portion right here. Alright? It doesn't include the origin. Well, its counterpart on the negative axis is going to look like this. Not too steep. Right, and we are revolving about the y-axis, right? We should get this solid right here. Hopefully it looks sort of 3D with these special effects, right? So that's what we want, this rotation about the y-axis. Let's see, so letter A. Considering y as a function of x, so no need to do anything here. So let me label A, y as a function of x. So y equals to x squared. We will need the derivative y prime or f prime, which is going to be 2x. All right. So in this case, in general, again, for functions of x, we have a formula that says big S equals to 2 pi integral from a to b of r of x times the square root of 1 plus f prime quantity squared dx. Alright, well, we need to define what r of x is. Alright, I mean the f prime, just take the derivative, plug it in inside of the radical. I don't think that's a really big deal. But this one, the r of x, is usually the trickiest one. Okay, in this case, because the rotation is vertical, from the axis of rotation to any point on the function its horizontal distance, it's x. Alright, so this means r of x will be simply x. But the question is x already a function of x? It is, right? So we don't need to replace that x with anything else. Alright, so let's just plug in for the derivative s equals to 2 pi from, and in this case, the limits of integration are pretty much given from 1 to 2. And that's x times the square root of 1 plus the derivative of x squared, which is 2x. The whole thing quantity squared. Be careful when squaring these 2x, because that power of 2 affects both the coefficient 2 and the x as well. So that's an x 1 plus 4x squared dx from 1 to 2. Okay. And well, notice in this case, no symmetry with limits of integration, so we're just going to integrate this one the way it is. Alright, so the best method to compute this integral, any ideas? U substitution. Yes, I think here is clearer about the U substitution, of course. So let's go ahead and do that. So U equals to 1 plus 4x squared du equals 8x dx, and of course x dx equals 1 over 8 du. And again, here I strongly suggest to change the limits, otherwise it's just going to become a mess if you do it the other way. But of course, I mean, if you prefer the other way, I'm okay with that. U evaluated at 1 and U evaluated at 2. So 1 plus 4 times 1 squared. So that's 1 squared, which is 1 times 4, which is 8. 1 times 4 is 4 plus 1 is 9. Wait, what did I say? No. 5. Yeah. And 1 plus 4 times 2 squared. So 2 squared, which is 4. Okay, let me do in slower motion here. 2 squared, which is 4 times 4, 16 plus 1, 17. It's weird because this is like the 5th time I do this problem, and I mess up this part all the time. I don't know why. Alright, so let me make this a little smaller and put it here. Nope, it's too far. Okay, so let me continue over here. So I'm going to need a lot of space for the other version of the problem. So doing the U substitution, this is 2 pi, the integral from 5 to 17. And from 5 to 17, and that's the square root of U with respect to U. Alright, so let's compute this integral. So, I forgot that factor, so that 1/8. And that 1/8 goes as a 1/4 outside with the 2 pi. u to the 1/2 du, and pi over 4 u to the 3/2 rather, over 3/2 from 5 to 7. 17, yes, 17. Whoops, I don't know why it's zooming in. 17, 17, 17. And well, dividing by 3/2 is the same as multiplying by 2/3. That's gonna give us, okay, 2/3 times 1/4. That's 1/6. So pi over 6 u to the 3/2 from, or radian. Okay, let me leave it like this. From 5 to 17. All right. So here is the thing. So this problem looks similar in terms of the property of radicals that we are going to use to compute this one. So in comparison with the problem we did before, the limits were perfect squares, right? In this case, neither 5 nor 17 are perfect squares. So in this case, I'm not going to use that property of the radicals with the power of x outside of the radical. I'm going to use the one that is inside, and I'll show you how. I will show you why. So pi over 6 square root of u to the 3rd from 5 to 17, and upper limit minus lower limit. 17 cubed, 5 cubed, and well, in this case, I'm going to break this 17 cubed and 5 cubed as 17 squared times 17. All right? So this is the same as 17 squared times 17 and 5 squared times 5. All right? And we can take the square root of the perfect square and leave the non-perfect square inside of the radical. And square root of 17 squared, well, that's pi over 6. 17 root of 17 minus 5 root of 5. Final answer. Funky numbers. Yeah, those are the kind of answers that we get for this type of problems most of the time. Okay, so that's one way. That was one way. Let me zoom the whole thing so you can see in case you miss anything, in case you have a question on any part, whether the setup, the integration, the simplification before moving on to the next part, or whether you're still catching up with writing it. Are we good to go with the part B of the problem? All right. Okay, part B. And for part B, x, no, I don't want to buy anything. X as a function of y. All right. Well, so let's start redefining our function. Y equals to x squared. So we need to redefine this function as a function of y. Well, to isolate the x, we need to do the opposite of squaring, which is the square root. X equals the square root of y, and I know you might be thinking, should we put that plus or minus because of the square root property? Well, technically we should, but in this case, since we are working only with the positive part of that parabola, we don't need to do this anymore. So What else? So from here, let's define this x as a g of y, and that's a y to the 1/2, and that's going to be g prime equals to 1/2 y to the negative 1/2, which is 1 over 2 square root of y when we simplify the radical. All right. And then, well, let's look at the region. So in this case, let's use the formula that involves that it's in terms of y. Well, so big S equals to 2 pi from C to D r of y square root of 1 plus g prime squared dy. All right. Okay, so number one, we're not rotating this about the other, or rather about the x-axis in this case. We're still rotating about the y-axis. This time what we have, it's still x, okay. The distance between the axis of rotation to the point, to any point on the graph, again, let me go back to, it's still x unit. It's still a horizontal distance that we will still call x. From C to D, x the square root of 1 plus g prime squared. However, in this case, we are working with functions of y. Is this x a function of y? So what is x in terms of y then? Isn't it this? No, not that. Actually, this. All right. So let's rewrite this finally as a 2 pi. Integral from C to D. Okay, what are the limits C to D? So we use the limits in terms of x from 1 to 4. Now we're going to use the new limits. We're given the limits in terms of y, which are 1 to 4. Adrian, you have a question?
Oh, no, since
We're going to say the limits 1 to 4. 1 to 4. And that's x in terms of y, which is the square root of y, times the square root of 1 plus quantity squared, and our quantity squared is 1 over 2 root of y with respect to y. All right. So a few algebraic steps here and there. Okay, let's square the number 1, which is going to be a 1. And the square of 2 radical y in the denominator, well, square the 2, that's going to give us a 4. And a y dy. Okay, so I'm leaving this space right here for LCDs. Whoops. This is technically a 1 over 1, and to combine these together, let's multiply numerator and denominator by the missing factor, in this case 4y combine into a single fraction, that's going to be 4y over 4y plus 1 over 4y. And well, in this case, I'm going to use another property of radicals in this case, because what do we have? We have the product of two radicals. We can group this into a single radical by having the radical of a product. That's going to be y times 4y plus 1 over y dy, and see how this cancel. That's going to give us simply 2 pi, the integral from 1 to 4, square root of 4y plus 1 dy. Alright? And the integral is a lot simpler than initially looked like. So let's see. I guess the simple U substitution is going to do it here. So let's see. Let's set up the U and the du part. U equals to 4y plus 1. Du equals 4 dy. And dy equals 1/4 du. Yes?
Wouldn't it be 1y plus 1 over 4?
Plus 1 over 4. Oh, yes. This one right here, I think I missed that part. Yes, thank you. So there's a 4 over here. And over 2. Alright, that cancels. Here as well. Yep. And so this will be okay. Yeah, let's change the limits again. U evaluated at 1 equals 4 times 1 plus 1, which equals 5, and U of 4, which is 4 times 4 plus 1, which equals 17. I think you're going to see the similarities here because we're getting the same limits of integration as before, and the U will look a lot like the same as well. So in this case, let's do the U substitution. So that's going to be pi integral from 5 to 17 square root of U times 1/4 du, which equals to pi over 4 integral from pi to 17 square root of U du. And well, why do double of the work? We already computed this integral in the previous part. Let's just copy the result. I will point out the two integrals so you can see it. 17 root of 17 minus 5 root of 5. Alright, same answer. So, okay, let me highlight this. So this is the integral that we do here. And this is the integral, where is it? Well, technically here, but with rational exponents. So again, regardless of how you define the functions, whether you're working with functions of x or whether you're working with functions of y, you should get the same result. The result changes when you rotate the region about one axis or the other. So that difference was discussed when we covered the first couple of exercises. This no difference idea is covered in this last example. All right.